A very, very good evening, members of SP Abuja section. Welcome to day two of our Student Affairs Skills Development Series, Real Talk, Real Topics. As usual, we kindly appeal that you share this link to all of your colleagues. Of course, we have 9 student chapters in Abuja section from ATBU to AUST to Nile University to Base University to BUK to Uni Abuja, of course, University of Maiduguri, Bayero University, Base University, all of our students. Please share this to your different student chapters because the next 5 minutes will start. Before we kick start, can you help me go to the comment section and drop a few quotes or a few tips you learned yesterday? What did you learn yesterday from Daniela Obaze? Just go to the comment section, write on the chat box what you took from yesterday's training. I'd like to know what you took from yesterday's training in the comment section. So I'll be reading it out as you share your key takeaways from yesterday's training. So please do me a favor while you're inviting your friends, while you're inviting your colleagues, kindly share on the comment section your key takeaways from yesterday's training. And then in 5 minutes, we'll kickstart the event properly. Thank you.
Afan, how are you? Can you hear me?
Okay, so ladies and gentlemen, welcome to our Student Affairs series, Fundamentals of PVT Analysis. Of course, the theme for today's event, Key Concepts and Applications in Reservoir Engineering. Of course, we are pleased to have some very amazing professionals from Cypher Crescent Limited who would be taking us on this amazing theme. Yesterday, we were so pleased to have Daniela, who took us through the introductory parts of this. And today we'll be having Olayemi Samuel, who will be taking us on the concluding part of this amazing theme. And so, of course, you can see the agenda we have for today. It's going to be very short, very interactive, and very interesting. Let me quickly continue by sharing the safety brief. Please, for the course of today's training, please, if you're not to speak, we appeal that you leave your microphone on mute throughout the course of the deliberation so that you may not interfere with our speakers. And just in case you want to ask questions, you use the chat and the comment box for your questions. And a speaker for today will do justice by responding to all of your questions, just like Daniela did yesterday. Let me continue by recognizing some amazing people we have on the call. I'll start by saying a warm welcome to our Student Affairs Chair who is on the call. A warm evening to you, Aisha Tuko. Good evening, ma'am.
Good evening, Afan. Thank you so much for this. Good evening, everyone. Thank you for joining.
Thank you, ma'am, for all of the amazing stuff you do for the students in SP Abuja section. We celebrate the tenacity of purpose. We also like to welcome, of course, the Assistant Student Affairs Chair, Chinyere Enwere. A very warm, Chinaza Enwere, I beg your pardon. A very warm evening to you, ma'am.
Thank you very much. Good evening. Good evening, everyone.
Yes, Chinaza, good evening to you. We also say one welcome to, of course, our trainee for today. The person training us for today is a graduate trainee from Cypher Crescent Limited, Ogundele Olayemi Samuel. A warm evening to you, sir. Confirm you can hear me.
Yes, I can hear you. Good evening.
Thank you so much, sir, for accepting to share your wealth of knowledge to students of SP Abuja section. Still on the call, we have a graduate trainee from Cypher Crescent who also did justice yesterday, Obaze Daniela. Obaze, good evening, ma'am, and thank you for joining us today.
Good evening. Thank you for having me.
Thank you, ma'am. We are so pleased to welcome all of our student chapters from ATBU. ATBU, if you're on the call, you can just drop a chat representing ATBU if you're from ATBU. AUST, we welcome you. If you're from AUST, African University of Science and Technology, you can drop a chat proudly representing AUST. ABU, Ahmadu Bello University Zario. If you're from there, drop on the chat, proudly representing ABU. Bayero University, BUK. If you're on the call, kindly do us justice by dropping on the chat, proudly representing BUK. Of course, if you're from Bayes University, do the same thing, repping Bayes University. You're from Foot Mina, please drop a chat on the chat box, repping Foot Mina. If you're from Nile University, please drop a chat, Nile University. If you're also from Uni Abuja, please drop on the chat, proudly Uni Abuja. And of course, the last but not the least, if you're from University of Maiduguri, please drop it on the chat box, proudly UniMed. Let me see, who is the first to chat? Oh, ATBU is the first to chat. Adeyinka Opeoluwa, thank you for being the first to proudly represent ATBU. Ladies and gentlemen, we switch gears immediately to the welcome remark, and this will be taken by no other than our Student Affairs Chair, Aisha Tuko Digi. Dear Aisha, would like to hear from you.
Thank you very much, Afan, for this. And thank you very much, Daniela, for yesterday's session. I'm sure, sorry, I was not, I couldn't join. I had a meeting. It was unexpected. So I look forward to this session, and hopefully we'll all gain from it and apply it in our various fields. Thank you very much.
Thank you so much, Student Affairs Chair, for that very brief remarks. Of course, we would gain so much from today's training. Again, you can see the synopsis for today's event. You sure will sharpen your technical edge with practical insights from industry-ready professionals. My pleasure to introduce Olayemi Samuel. Of course, his profile is on the screen. He is a first class. Please, can you give him some virtual applause? It's not easy to have a first class graduates train you. First class graduate from Petroleum Engineering from Bayero University, Kano. That means he's even SP Abuja section. Amazing. Where he graduated as the joint best in his class with a CGPA of 4.83 out of 5. He also holds a national diploma in minerals and petroleum resources engineering from Kwara State Polytechnic, where he finished with distinction as the best graduating student. Please, can you give some virtual applause, please? Passionate about technology-driven innovation in the energy sector, Olayemi is particularly interested in leveraging artificial intelligence, machine learning, and data analytics to improve reservoir estimation, production optimization, and carbon capture and utilization CCU. Currently, he is a graduate trainee at Cypher Crescent Limited, where he contributes to the development of AI-powered solutions that enhance oil and gas operations. He is skilled in Python programming and utilizes industry tools such as Prosper for production simulation and analysis. Olayemi excellence has been recognized through several awards, including Best Graduating Student in Petroleum Engineering BUK. Please celebrate him. The Pesetas Club Scholarship. Please celebrate him. The Petroleum Technology Development Fund in-country scholarship. Please, a round of applause. He has also demonstrated leadership as the technical team lead of the SPE BUK student chapter. Of course, Abuja section is the section of excellence, organizing, training, and leading teams in completions. Beyond his technical skill, Olayemi enjoys personal development, mentorship, and football. Today, he is showing us how good of a mentor he is. Ladies and gentlemen, help me welcome the graduate trainee from Cypher Crescent, a one-time best graduating student from BUK here in Abuja section, Ogundele Olayemi Samuel. Welcome, sir. Over to you, sir.
All right. Thank you for having me here. It's a privilege to be here and doing this for the section I owe there into my close to my heart, Abuja section. So uh, I've always been part of Abuja section and I still remain part of Abuja section. So it's a privilege to be here once again through my company. So I hope your time here with me today, you learn 1, 2, or 3 things about PVT that we are all talking about since yesterday. So I want to say just a big thank you to the section chair in our absentia, Dr. Ikechukwu, and the student affairs chair here. So I want to say a big thank you, and also to the CEO of to the CEO of Cypher Crescent Limited for this opportunity to give back to Abuja section. Thank you. So we'll be going ahead while I share my screen. So I'll go straight to the business of the day. All right, just give me a moment. Let me try to. Please, if you can see my screen, confirm. See my screen?
Yes, we can see your screen. Yeah.
All right, so this is the day 2 of the fundamentals of PVT analysis. And as been introduced earlier, my name is Olayemi Samuel Ogundele, a graduate trainee here at Cypher Crescent Limited. So today we'll be talking more, just building on what my colleague has shared yesterday. We'll be talking on PVT parameter and the trend. Then how do we get the sources of this PVT data? That we look at more sources of this PVT data, then we try to look at elements of PVT report in such a way that when we see this PVT report, we'll be able to identify it and then know what it actually entails. So of course, there will be enough room for question and answer to clear all your doubts about PVT. both from yesterday's section and today's section. So I would like to have a brief recap of what my colleague shared yesterday. So it was reiterated that petroleum is a complex mixture of hydrocarbon and other minor constituents. These minor constituents can be nitrogen, carbon dioxide, hydrogen sulfide, and the like. So the these properties that we're actually talking about is very, very, like, it varies and it depends on the various composition, various type of hydrocarbon. It varies depending on that various type of hydrocarbon and other constituents. So the knowledge of this physical property is very, very essential in just not only reservoir engineering, it's also very, very essential in production engineering and also the petroleum engineering sector at large. So we talked yesterday also, we talked about PVT analysis, which is basically understanding the fluid behavior, dynamic behavior of fluid in the reservoir. So this behavior, this fluid depends on different, respond to different conditions. Although we assume to have a constant temperature, but it responds to different pressure condition in the reservoir. So we are also to look at the relevance. Where is it even coming? Why do we really need to even study this PVT as the case may be? So we'll talk about reservoir simulation. We look at material balance calculation, which we're able to estimate our reserve appropriately. So we need the knowledge of this PVT to do that. Then we talk of wellbore hydraulics, where we talk of viscosity, density that will allow us to understand our pressure regime, our wellbore storage, and all the likes. Then also we talk about apart from that, we'll also talk about the sampling. So when we talk about bottom-hole sampling, the surface sampling. So bottom-hole sampling basically is done using specialized tools to get a representative sample. I'm making an emphasis on this representative sample because if we cannot get this accurate sample collected from the bottom hole, so it is our PVT, all the information we are going to get from the PVT is going to be very, very maybe wrong. And this, we wouldn't want to, we are still in the stage of estimating our reserve. So we wouldn't want to give a false impression of what we are giving out, because whatever we decide from that PVT analysis may help is what is going to help determine various activities that is going to take place for that. That is, it will help us to design the kind of facility we want. It will help us define the kind of things we actually need to put in place to recover our oil. So obviously, you don't want to give that false information because it's going to be detrimental to maybe wasting of funds. Let me just put it that way, if you're not giving out the correct information. So we have to take that representative samples, and before we can do that, we condition the well in such a way that we lower the flow rate, and to cancel out any pressure imbalances. Then it is advisable, though this can be taken during production, not during production, but during, we can shorten the well at any point of production. Then we shorten the well. We allow it for around 24 to 72 hours before we take a sample. So that is it. Though this one is more costly, that's sampling from bottom hole. Then the other one is surface sampling, which we can either do at wellhead or at separators. So the separator is the best go there, because it's only in some situation whereby we our separator, maybe chemicals has already been added at the separator, that we need to come to the wellhead and do something, because there are a lot of things going on at the wellhead, like turbulence flow, different kind of flow. We will not have that, and when all those flow is happening, we'll not be able to get the representative sample. So in a nutshell, taking taking sample from that surface, we need to consider taking it from the separator. Then other things that will be done later is just trying to do the recombination. And also lastly, the thing that I was talking about yesterday was the volumetric properties of the properties of thermophysical properties of the PVT, which we were made to understand that it can either be volumetric properties, it can either be transport properties or thermodynamic properties. Volumetric properties when we're talking of formation volume factor, which can be formation volume factor of either gas or oil. Then we talk of density, under the volumetric properties, we talk of density and the likes. Then on the transport property, we talk of viscosity. Then lastly, on the thermodynamic properties, we talk of just Thomson effect and enthalpy, entropy, and the likes. So today I want you to open your mind and be ready to learn as much as possible. So that's just a brief recap of all the thing that was discussed yesterday. I may not be touching on anything, but at least if you were here yesterday, I know you gained more than that. So it's just me giving a brief for the sake of people that are just joining on for the first time and to establish the fact that this is where we have to move forward from there. So to make this class as interactive as possible, if you have any question, okay, you can drop it in the chat, but I think I will pick it up from there. And if you need any clarification going forward and you think it cannot wait, maybe I can also take that during the call by you raising up your hand. So yes, I don't know. Maybe you can just, I don't know if I can see the chat, but here you can just drop what exactly you are expecting from this session today. Just drop one thing you are expecting, or just give a thumbs up if you are ready to go. Let's do it that way. If you're ready to go, give me a thumbs up. Let's see how many people are actually ready to go. Are there any? I'm not seeing any thumbs up. Is there anyone? Oh, okay, I think let me see if I can see. Okay. Okay, so someone requested I should be more audible, so I will do that. So to learn everything you have for us. All right. So going forward, our icebreaker section is have you seen anything like this before? Let me see your reaction or something similar to this. Have you seen it? Have you seen this bottle I'm showing? Have you come across it before now? Am I still not audible? I'm not seeing any reaction here. Okay, someone said, sure. Okay. So please, I would love us to be very, very interactive. So I don't want this to be just like a normal presentation I will go. So we need to go with the flow. We need to carry ourselves along. So, and the person that said sure, or to everyone that have seen it, but we are not talking. So when you try to open this bottle, this a soda, it may not necessarily be a Coca-Cola product, but any carbonated soft drink. So what did you notice when you tried to open it at that point of contact with it? So okay. Okay, wow. I love that. Someone said, shh, yes, that's the sound I used to hear too. Okay, gas escapes, okay. I think you are taking it a, a bit further to where we are going to. So without wasting time, okay, I think gas escaped. Okay, yes, fine. You're correct. So now, if you don't have any bottle of Coke close to you, if you have any bottle of Coke close to you, you can just try to check that out. And if you don't have any, maybe at the end of this section, I will be one to anyone that doesn't have. All right, so this is the fact I'm trying to establish here. So let's just imagine this sealed Coke as a reservoir. Let's just imagine it being a reservoir. So at this point, before you open it, so and yesterday it was established saturated and undersaturated, and I believe by now we know what saturated and undersaturated is all about. So to back to our memory. So that's why I'm trying to use this analogy. So when the pressure is greater than bubble point pressure, so it is established that the phase is one phase and it is undersaturated. But any pressure below the bubble point pressure is saturated. That is, there is presence of more than a phase. So what happens with this bottle of Coke is at this point in time, it can be as it is like this, it can be represented that this is a single phase because we are not seeing any bubble of gas at this point. We are not hearing any sound of that gas escaping. So at this point in time, it's very it can be considered as a single phase undersaturated, as the case may be. So at the points where we're trying to open this bottle, so that is trying to deplete the pressure. You start hearing those sound until you completely open it. Then at some point you begin to see a bubble of gas coming out of that Coke. That is we can also relate that to a bubble point pressure, where that is the highest pressure in which you first experience the liberation or the bubble of gas, as the case may be. So that is that on that. So I just want us to understand the concept of undersaturated and saturated. That is because it's going to help us a lot going forward in this training. So moving forward, now we talk about those PVT parameters, right? And I've tried to recall to bring our attention back to what it is. Now, the main point here is when you see those PVT curve, you should be able to identify it and know exactly what is happening with it, because you maybe at some point in time you may want to obviously you want to get into the industry, and maybe some recruiter might just bring up all those kind of curve and tell you to identify it. So at the end of today, you should be able to see if each of these curve from this PVT parameter actually represents. Although everything at a constant temperature, everything is almost everything is not almost everything there is a function of pressure, because we are trying to see how our fluid behave under different kind of pressure. So now I will be starting with this. This is a oil formation volume factor against pressure. So, and it was established yesterday that oil formation volume factor relates the volume of oil at the reservoir condition to the volume of oil at the surface or standard condition, as the case may be. So it's just a conversion, I will say, is a conversion factor for what we can actually get from the reservoir and what is actually present in the reservoir and what we can get to the surface. So let's do just a little bit for our understanding. Let's do a little bit of um, maybe calculation here. So let's assume at the reservoir. So don't forget the upper part of it is the volume of oil at the reservoir condition. Let's assume we have like 20 barrel of oil there. Then at the surface, so we now want to, so at the surface, we have 11 barrel, as the case may be. So what is this telling us is now we have this 20 barrel of oil at the reservoir, but what we are getting at the surface is just 11 barrel. Some things might have actually happened, and you may be wondering that what has happened. Yes, we established the fact of what actually happened, why we are getting the 11 barrel as the case instead of the 20 barrel. Obviously, we cannot get everything to the surface as oil. So now let's go to this trend. So I love to read my charts from this end because, okay, it's my eraser. All right, so I love reading my charts from this end and to this end. So there's a reason for that. Okay, like this very point here is established to be your initial pressure in the reservoir, at the reservoir rather. So this is the pressure at the reservoir. That is your initial pressure. And like I said earlier, all this region from here to here is one phase. That is only oil. We believe that is only oil that is present there, but there's more to that. So it's oil formation volume factor above PB, and I said is an undersaturated, only one phase present. And what is happening here now, as this pressure here decreases, so going forward here, this will represent our PB. That's the bubble point pressure. So any region above this is undersaturated. Region below that is saturated. So now, as the pressure goes from initial reservoir pressure condition. So what happened here is you believe that oil oil does not actually exist on or just like that. We just want to the fact that we say is a single phase, that doesn't mean that oil is not in that gas is not in that oil. So what happens as this pressure decreases is that as the pressure decreases, you see that there's a slight change, slight increment in this oil formation volume factor. Why? The gas in that oil begins to expand as we decrease the pressure. So this take us back to our Boyle's law. At constant temperature, the pressure is inversely proportional to volume. So as the pressure decreases, volume increases. So that's we have we have gas inside this, and that gas is what is trying to we are trying to reduce the pressure. Then the gas begins to expand, making the oil present there to be increasing. So that's basically what happens there. So you keep increasing up, it get up onto the to this point. So at this point is, like I said, this point is bubble point pressure, and that is the highest pressure in which we first notice that bubble of gas. Although this is oil formation volume factor, then in the case that is gas, so it's going to generally is being considered as a saturation pressure, which in the case of oil is called bubble point. That's the first bubble of gas coming out of oil. Please confirm you can still hear me.
Yes, we can hear you, sir.
Please confirm you can hear me.
Yes, we can hear you, sir.
All right. All right. So the other case is all right. The other case is I said saturation pressure, which can either be bubble point pressure or dew point pressure. So the dew point pressure on the other case is the pressure at which the highest pressure at which the liquid of gas we notice the liquid droplets in gas. So that's the case of it. So this point particularly is known as saturation pressure. The pressure at this point is saturation pressure, but like you can see here, we are dealing with oil formation volume factor. So that's why I keep using bubble point pressure. So like I was saying, at this point, the first bubble of gas evolve. Then moving downward, you see that this trend behaves differently. Why? Now, the gas that is making this to increase, the volume here to increase, it begins to liberate, it begins to come out of that oil. So hence, it makes sense that the volume of oil begin to decrease. So going forward, further, then as you're decreasing that pressure, the volume begin to reduce. That is, oil formation volume factor begin to reduce till it get to this point. That's just a point above 1.05. And that is exactly what happens here. So as you are producing, this is the initial thing you have in your reservoir. As you are producing, so as you are decreasing the pressure, the gas in that oil begins to come out of it. And in some cases, in the reservoir, it begins to form gas cap. So that's what happens, that we can not actually get the exact 20 barrel of oil we expected, and we are getting 11. And you can see that the value of BO cannot be, will always be greater than unity, that is greater than 1. So when it is 1.0 to 1.1, that's heavy oil or this asphaltic oil. When it is black oil, we have the range of BO to be 1.0 to 1.5. Then when it begins to be volatile, like volatile oil, that's 1.5 to 2.5. Then anything above 2.5, we begin to have critical oil, that is oil close to being completely gas. So that is exactly what happens to this trend. So basically, as we are decreasing the pressure at one, the gas in that oil begins to expand. Then we notice a slight increase in the volume of the oil. As the oil begins to evolve out of heat, then our value of BO begins to decrease. So that is exactly what happens here. So moving forward, we will look at another graph. This is graph of gas solubility, or in some cases it's being called gas oil ratio. And what is this gas oil ratio? Gas oil ratio is the amount of gas that dissolved in one stock tank barrel of oil at prevailing reservoir condition, that is pressure and temperature. So what happens here? This behaves differently. We said what happens here is from this end to this end. So there's this law, Henry law, that says the volume, excuse me, this Henry law says that the amount of gas that dissolved in oil is directly proportional to the partial pressure of the liquid above that oil. So that is exactly what is happening here. So that gas, at this point in time, the gas is completely dissolved. And what we are trying to look at is the amount of gas that dissolved in that oil. So now, at this point, from the initial pressure here, the amount of, at the initial pressure here, so up onto the bubble point pressure, we notice that the solubility is constant. So nothing leaves the oil. So the gas solubility, okay, gas solubility remain constant. So the out onto this bubble point pressure again, that is where changes begin to happen. And what is the changes? As the gas begins to evolve, moving out of that oil, the value of amount of gas that dissolve in that oil begins to reduce. And that's, from the definition, is the volume of gas that dissolved in oil. So it makes sense for it to keep to be reducing. So that is exactly what happens to this trend. So like the soda bottle that was used as an illustration earlier. So at high pressure, gas dissolved. We have high gas solubility. Then at low pressure, gas come out. That's exactly what happens here. The RS decreases. That's basically what happens here. So when the soda bottle is completely close. So it is expected that the oil is the gas is completely dissolved in there. So moving forward, we'll be going to the, okay, going to the next trend, which is the density. Density is just the ratio of mass on volume. So mass of oil over volume of oil. So this graph behaves differently. This is initial pressure. And I said I love interpreting from the right hand side to the left hand side because it makes sense that because as we are removing fluid from the reservoir, definitely the pressure is depleting. So now at this point, we believe this is also still the same fact that this place is undersaturated, that is one single phase, and oil is completely dissolved in there. And density is mass on the ratio of our mass to the volume. So now, and this relationship supposed to be, the relationship supposed to be as density increases, the volume supposed to decrease. But here, what is happening here is that the gas that completely dissolve in that oil, it makes the density of that oil to be lighter because there's gas present in that oil. So generally, the oil will be lighter. And as we're decreasing that pressure, that's what makes this trend to come down. Then when gas begin to evolve, that's our bubble point, where gas begin to liberate out of that oil, our oil becomes denser. That is, as the gas leaves, the oil becomes heavier, 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 and moving forward like that. That's exactly. So most importantly, if you can identify your bubble point pressure, every other thing that happens at the left-hand side of the graph or at the right-hand side of the graph, it's very, very easier to identify and to know what exactly is happening there. So for crude oil, API is the standard we use to compare for specific gravity of oil, it's relating the density of oil to the density of water, and API is the standard being used. So API gravity ranges from very light oil, which is around 47 degree API, to a heavy oil, which is around 10 degree API. So I won't be dwelling much on this other property here, because if you take a look at that trend, it's almost similar to what happens in density. And viscosity is the resistance at which the fluid flow. So as we are decreasing the pressure, yes, we have gas in here. So the gas makes it less dense, so it can flow. So it makes sense that the trend begin to decrease here. Then when gas begin to evolve out of that oil, then the trend begins to go up in the sense that oil is now heavier. So as pressure, that's two things happening there. As the pressure is being decreased, the gas evolves below the bubble point, then it becomes heavier. And also, when you have a less pressure to push the oil, to definitely the oil is also very, very dense at this point. So the flow will be restricted. So there are other proper parameters. So I just want to take my time to explain these four parameters, because if we are able to get these other parameters, we can just look at it on a later time. Maybe look at gas formation for volume factor, and also look at the other one, which is compressibility. So moving forward, I want to talk about the sources of PVT data. So it was established yesterday that we're collecting this sample, and those samples that we're collecting, what do we do with it? We're collecting sample from the bottom hole. We're collecting sample from surface. What do we do with it? Why are we collecting the sample? So it's collecting the sample equivalent to getting those parameters without doing anything with it. So that's why we have to take that sample collected into the laboratory. And taking this to laboratory, we can actually get the parameter we're looking for, such as BO, that's oil formation volume factor, the gas solubility, RS, the density, the bubble point pressure, most importantly, and the likes. So now there are a lot of tests here that is being carried out in the laboratory experiment, but we'll be talking about just three here, which is the basic ones, the routine one, which is a constant composition experiment. In some cases, you see it as constant mass study. Then depletion experiments, which it can either be differential liberation experiment or constant volume depletion. Then the other one is separator test. There, yes, we have other tests like shred test. You might have come across that, but that is not because that is necessary when we want to do further study, maybe enhance recovery. But this was the basic one that is needed in the beginning of our study and to understand what our reservoir looks like. So another one source we can get. So now, if this laboratory experiment is actually limited to in such a way that some of those pressure points, we deplete those pressure just bit by bit, then what if we need to get more information about a certain pressure points that laboratory experiment did not cover? So that's when we use black hole modeling, which is a model that people has already established. So it's basically classify reservoir fluid into liquid and gas. So it's not taking into consideration all the other components. It's just saying this as either liquid or gas. Then it uses correlation that to get PVT parameter, like I said, for those pressure points that was not stated on our laboratory experiment. So example of this, so for all those parameters, there are correlation that we can use to get those information. So one of the most of like some of the common one is Glasso, we have Petrovsky, we have Standing, we have Almaron, we have Vasquez-Beggs for each, and it depends for each and every parameter. So you can see here, black oil modeling does not expressly depend on the results gotten from the laboratory experiment. Okay. So now the next one is a compositional analysis. So this uses equation of state to estimate PVT parameter. Yes, almost similar to this. Those pressure points that we cannot get, we can use equation of state to establish, to get those PVT parameters. So now, one of the most important things to even get to using this equation of state is characterization, which you might have come across. Maybe you are seeing a composition of reservoir fluid of hydrocarbon, and you are seeing somewhere you are seeing C7 plus, you are seeing C32 plus. So this is what we take into consideration the that lump sum, undefined lump sum of that hydrocarbon, that is all those C7 plus. You want to, from that C1, C2, C3, C4, C5, you're able to see what each component, what each of those C1, C2 contains in terms of mole fraction and every other thing. So you need this characterization to break down those C7, C plus, C maybe C7 as the case may be, or C32, C20. So all those lump sum, you need characterization to break it out. And what do you need for this characterization? You need input from laboratory experiments. You can see that this line is not broken, so as compared to this. So this compositional analysis depend on the information from laboratory experiment. So you get like mole fraction, your specific gravity, that's the input you use to get information for equation of states. So example of this equation of states is their regas, your normal regas that you know, that's it. Then the Van der Waals. Then in petroleum industry, we make use of Ben Robinson, Lee Kwang, as these, which are basically called cubic equation of states. So in a nutshell, so black oil modeling does not necessarily depend on the results gotten from laboratory experiment, but compositional analysis depends. We get information to even go ahead with compositional analysis through laboratory experiment that has been conducted earlier. So that's that on that. Now, we begin to look at this test that we discussed earlier. So the first test here is constant composition experiment. After you might have taken your samples, you bring it to the laboratory, then you insert that sample in a PVT cell, which is what you are looking at here, at this figure here. So we are putting this, this is pressure that is provided. Yes, I said we need to get this sample, like very, very a replica of whatever we have in the reservoir. And we want to get it at 100% oil, that is undersaturated single phase oil. So that is what it is being done here. But before this stage, there's what we call validity check. A lot of things might have gone behind here to ensure that what we are getting is actually what's in the reservoir. So now, after getting it into the PVT cell, then there will be a pressure support, which can either be mercury and any gas. So now I would like to use a clock here as an illustration here. So this, let's say this is my 4 o'clock. So what happened here is at this cell, you ensure that you raise the pressure of this cell, this particular cell, above what you have in the as your initial reservoir pressure. We established yesterday that you have the knowledge of your initial reservoir pressure even before you start doing all this. So you raise this slightly above. Let's assume your reservoir pressure is 4,000. Let's assume, just as an assumption. So you want to raise the pressure here. This is a pressure gauge. You want to raise it to like 5,000. So as you are coming, you don't want to start from the reservoir pressure. So you want to get some consistency before you even get to the reservoir pressure. So how does this work is after that, placing all this, then you begin to reduce the pressure. As you are reducing the pressure, you are measuring the volume of what is there. Then that's the pressure has been reduced to around 1 o'clock, and the oil is still 100%. Then you reduce again to around slightly something before 12. Then what happens here? You can see this yellow dot. What happens here is that there is this bubble of gas, which which makes sense as we are decreasing the pressure. Remember that graph? As we are decreasing the pressure till like going forward, you will get to a point where first bubble of gas is being liberated out of the oil. So this is exactly what happened. And this experiment is very, very important because that is what will help us determine our bubble point, and which is exactly what happened in this C. So the bubble point is being determined here. So, and it is going to be recorded because this is very important to serve as a benchmark for most of the things we're going to do, the analysis we're going to do. So going forward, you still want to deplete the pressure and see all this relative volume gotten from this. You keep depleting it till it gets to atmospheric condition. That is your 14.7 psi and a 60° Fahrenheit. So that is where you stop. So like I said, the sample is kept at reservoir condition, constant temperature, and pressure above the initial reservoir pressure. The pressure is depleted in steps, like has been discussed. The total volume is measured at each pressure step, which represents our relative volume. So that is that about constant composition experiment. So the most important thing we want to get out of here is our bubble point, which is very, very important to whichever thing analysis we're going to do going forward. So another test is differential liberation experiment. So the difference here is that you still use your PVT cell, but now instead of you starting at pressure above reservoir pressure, now we are starting at bubble point pressure. That's why I said constant composition experiment is very, very important. So this will be where we are going to start our differential liberation experiment. So at that constant temperature, we're still using constant temperature, then at the bubble point. So it's just basically what we are doing here on constant composition. We will keep reducing the pressure, then the gas at bubble point, gas has been coming out of oil, right? So continually, as we decrease the pressure, the volume, the gas begins to accumulate. Then we measure this gas. We take out this gas. And one thing I forgot to mention here is constant composition experiments. Yes, and you might be wondering why, because nothing is being removed out of till this experiment is being completed. So it's constant composition. Whatever it is inside in the beginning of the experiment, that's what remains inside till the end of the experiment. But here, as the pressure is being decreased, you collect, you allow the gas to come into equilibrium with the liquid, you collect it and you measure it as your RS. That's a gas solubility. Then you keep on doing that, measuring the volume till it gets to atmospheric condition of 14.7 psi and 60 degree Fahrenheit. So now you also get your value of BO here by taking the volume here, dividing the volume here with the volume at the initial stage. That is, you can take the volume here and divide it by the residual volume. So you get your BO for each pressure step also. Sample of residual fluid at PB and reservoir temperature in the laboratory cell. Yes, pressure reduction instead causes gas to vaporize. Yes, we've discussed that. Liberated gas removed. Yes, remaining volume calculated. Yes, then residual oil determined at atmospheric pressure 14.7 and 60 degree Fahrenheit. Please, if you are following, just do thumbs up. Let me see how many of us are actually getting it. Then, if you have questions, you can keep dropping it in your chat in the chat box. Or if you are following, let me see your thumbs up. Is there any thumbs up? I can't see anything from here. Okay, you can also drop it in the chat box. Okay. Thank you, Abayami, for following. So moving forward to the next, like I said, we are basically discussing for the laboratory experiment, we are basically discussing three tests. We've discussed constant composition experiments, we discussed differential liberation experiment. Although I'm not going to talk about that. There's for this depletion experiment, there's also constant volume depletion. That is when we're trying to look take maybe we're dealing with gas samples. So we're not going to discuss that here today. So let's go to the next, which is the separator flash test. So this sample of the residual fluid is also collected at bubble point pressure and the reservoir temperature in the lab's cell. Then what happens here is you expel those oil then into the first step. So this separator can either be, this is two-stage separator. It can be more than two-stage separator. In some cases, you can just do one stage. So what happens is you take that sample at bubble point pressure, you begin to appreciate why bubble point pressure is important because it actually goes with the flow of what we are going to do. So you at bubble point pressure and you expel those fluid into your first separator. And we're using, instead of reservoir temperature, you are using the separator temperature here and the separator temperature conditional pressure. So when what happened here also is the gas out of that separator is being collected and measured. The oil is then sent again to the next stage of the separator. Now, for the second, just two-stage separator, we are handing it at a stock tank condition. So the surface condition in this case. So whatever is remaining here is your residual oil. So also, like we did for differential liberation, you get your BO through this and you get RS, which is your gas solubility by taking out this gas and measuring it. Then also, that is that on that separator or test. So like I said, sample of reservoir fluid that is bubble point and in the lab cell, the residual oil is oil expelled through sequence of flash vaporization. Like this case, we have to, in the first stage, the vaporized gas is removed and the liquid to the second phase flash. So it's also called flash test, as you can see from my screen there. So the stock tank oil volume determined at atmospheric pressure and 60 degree Fahrenheit. So at surface condition. So now all those experiments being discussed, okay, all those experiments being discussed, these are the key parameters you get from there. For constant composition experiments, you get your bubble point pressure, which is yes. You also get your oil compressibility. You also get the value of your oil density. Then for differential liberation experiments, you get formation volume factor of oil. you get gas solubility, you get oil viscosity. Then for separator test, you get your values of BO, RS, and oil density. Now, you can remember that my colleague established the fact that one of the important of getting this information, this parameter, is to be able to use it in a material balance equation so that we'll be able to estimate one of the way we can estimate the reserve we have. So now, this is I know few people or almost everybody here may be familiar with this equation. This is typical material balance equation. So where do you think, how do we get information for MBA? Why am I asking this? If you can look at this formula very well, you know that you need information such as BO, you need information such as RS, you get. So now, going back to this, for differential experiments, we have value of BO and RS. Then for separator test, we have value of BO and RS. So which of these do you think, or not which of these, what do you think we can use, or what is basically being used for material balance equation? So how do we go about that? If you have any idea, just drop it in the chat box in just a minute. Let me see if you're actually following, or if we, please drop it, drop it, drop it. A quick one, just a minute. No one is dropping anything. Are we following? It's just that, okay, which of those value of BO and RS you will want to use as a petroleum engineer? Let me put it that way. Okay, I'm not seeing anything in the chat, so let me just move ahead. So what we basically do here is we can't just directly pick from DLE. We can't just directly pick the what is it called? The separator values. So what we basically need to do here is trying to do adjustment. And now what are we adjusting? We are trying to adjust those parameters from DLE to and the separator. So we're finding a way of combining the two, because DLE is just like the lab simulation of what is happening in the reservoir. We're just trying to get what is happening. Then this separator actually gives us models what actually happens, because in this separator we'll be able to, all this information gets in for separator, we'll be able to model our facility. We'll be able to model our facility. Come back to that. So we'll be able to model our facility through what is it called? Sorry, I'm trying to. So we'll be able to model our facility through information gotten for the separator. So it's aid the design. So now we want to actually make prediction. We want to make $1 million of prediction, because whatever, as a PVT expert, whatever decision you're going to make is going to make or mar your company, because you wouldn't want to give a situation whereby you under predict, and at the end of the day, a facility is being built for that scenario, and what is expected to come out of the reservoir, or what is actually coming out of the reservoir, is beyond that. Or at the same time, you overshoot your shots, like maybe you're just second guessing. At the end of the day, what is inside maybe the reservoir, the well is actually empty. Actually, during my internship, I actually partake in one drilling of a well, and at the end of the day, the well is empty. That's a very long story on its own, because a lot of work has been done to the point of casing. So that is that on that. So coming back to where we are now, so we need to do some adjustment, and that adjustment we can do it. So now, using this formula that has already been established, correction of oil formation volume factor above bubble point. So what we'll be looking at is the bubble point, this BOFB multiplied by relative volume. This is just the bubble point oil formation volume factor at the flash. So this is at the separator. You multiply it by its relative volume. And what is this relative volume? Is volume at a certain pressure to volume at the bubble point. So bubble point is just like a reference point here. So you use that above bubble point, you use that to get your value of BU that you're going to insert here. Then below bubble point, you use bubble point, same bubble point oil formation volume factor at the separator, which is the F is for flash, denote flash, and is also known as a separator test. Then multiply by differential liberation oil formation volume factor, then divided by bubble point differential liberation oil formation volume factor. So if time permits, I will quickly show where we can actually get this sample of PVT report. So current adjustment for RS, this is being developed by Tariq, and this actually has a limitation, and the limitation is it works best under at a very high pressure. So when you are trying to reduce the pressure, the value of RS becomes at some point you begin to see negative value, which is very, very wrong. When you are seeing negative value, you should know that something is wrong with your with whatever you are trying to calculate. So in order to combat that, then another set of people led by McKin also propose another solution where we can actually get the value of RS by combining DLE and separator results to this basically address the value error gotten as a result of low pressure. So this is more accurate. So I will quickly rush. Don't think I have enough, more than enough time. So I will quickly rush on black oil modeling. So I've talked about a bit of it. So like I said, those are just routine PVT laboratory tests. So other sources we can also get this PVT parameter is through simulation. And through that simulation, black oil modeling is one of them, where we talk about different kind of correlations. So it uses correlation to get the PVT parameter of unknown pressure points, as I said earlier. So we want to, maybe we have a 4,000, the next one from our lab test is around 4,2. So if we want to get information between that 4,000 and 4,001, so we can use a black oil model. That is the model that has already been established. So like I said, we have Glasso, we have Standing, Petrosky, Fashad, Vasquez, Ambeg, Marons also. So all this, for viscosity, we have different black oil model correlation. For bubble points, we have separate ones. We have for BO, we have for RS. So we can actually read more on that. And this is just an extract of for standing, we have oil formation volume factor. So for standing, also have for bubble points determination. So wear temperature, degree Rankine, and the gas solubility is RS, as you know. So now for also Glasso has its own, Petrosky has its own, and the likes. So that is that the black oil modeling. So you can see that these formula are very, very long, and Sci-Fi Crescent is a technology company. So I'm currently writing, if time permits, I can quickly show you that code to you that I'm actually computing all this, that we can actually use it, just a normal Python code that we can actually use instead of going through calculating and pressing all this long this formula. It makes me sick anyway. So that's why I'm trying to make life easier for everyone, including you that are interested. So next one is the equation of state modeling. So an equation is a function that relates the properties of pressure, volume, temperature, and molar amount. The example of this equation of states, I've stated it earlier: the real gas equation, the van der Waals, and the Worms, the cubic equation of state, as they publicly call, which is very, very common and very, very used, mostly used in petroleum industry. They are Peng-Robinson and Swab-Redlich-Kwong equations. So And doing this equation of states, like I said, also is just trying to get more information um, for the pressure points that are not in existence from our laboratory experiment. And then I established the fact that this equation of state actually needs information from the laboratory experiment. And that's one of those mole fraction, because composition analysis is going to be conducted where you can get your mole fraction, the mole fraction, then the specific gravity. So you need that for your characterization. Then for your characterization, you'll be able to get the critical properties such as petroleum pressure, volume, and temperature. Then further, you get BO properties, you get the properties such as BO, RS, and the like. So these are the steps in carrying out this equation of state modeling. So most importantly, you do fluid sampling, bottom hole, surface, whichever case. Then you take it to the laboratory for your PVT analysis. Then the next thing you want to do characterization. Yes, we discussed earlier that you want to unpack what is inside that lumped sum of undefined hydrocarbon, that is C7 plus, C20 plus, C36 plus, as the case may be. Then equation of state model. This is where you choose the model you want to use. So basically, maybe you want to choose Speng-Robinson, you want to choose either Redlich-Kwong equation. Then at the end of the day, there's established information already through your laboratory experiment. You remember that you have your BO, you have your RS there. So you want to do tuning, you want to do matching. That is, you want to make sure that this is very, very close to what is obtainable from your laboratory experiment. Then after that, you get your PVT prediction, such as BO, RS, density, specific gravity, and the likes. So also, apart from getting more information on different pressure points, you also get from this, you also get to use it for quality checking. You could remember that someone asked a question yesterday about recombination. So for you to know that your recombination actually works well, so you use this equation of state modeling to also quality check whichever thing you are combining. So this also works beyond just determining more properties. It's also used as a tool which can be used to do quality checking. So now briefly, we want to see how PVT reports what it actually looks like. So it's going to contain accompanying information when you come across one. So though this is not general, so it depends on the company that is handling your report. So, but you're most likely going to see these sections on your PVT report: the company information, the general well information, maybe it is Shell that is doing it, maybe it is what's this place called now? So any company that is doing it, maybe then your general well information, maybe you get your information from a particular well involved field in Norway or anywhere. So all those information will be there. Then summary of PVT data, everything that has been done is going to be summarized in a page. You're going to see that. Then sample validity check. Like I said, you need to make sure that your sample is a representative value. So they are going to conduct a test just to ensure that whatever you are taking to the laboratory, this sample you are taking to the laboratory is close as possible to what you're having in the reservoir. Then the fluid composition, that's the composition of the fluid, C1, C2, other impurities that may be there. So the composition of those, then the constant composition experiment, there will be a section for that. Then DLE, depletion, differential liberation experiment, or constant volume depletion, depends on the kind of experiment and the kind of fluid you're working on. Also, separator test, then you have different kind of nomenclature, like all those appendices, you have different information. So at this point, I don't know if I can quickly share. I don't know how much minute I have. If I can quickly go through, I have a PVT sample here so that maybe all this information being discussed should be able to identify them there. So just flip through the pages there. So before the key takeaway. So let me see if I can share that. I don't know if I need to stop sharing this. Okay, let me reshare again. me share my entire screen now to make it better. So I believe we are, this is not what I want. Let me share it one after the other. Then it's my PDF. Excuse me, just a moment. Okay, I think I've seen it. So this is a PVT report done by Reservoir Laboratory. So these are as discussed, the element. This is just information about the company, final report, PVT analysis of MDT, or a sample from well 15. So this one is carrying that well information, 15.9 of Volve feed somewhere in Norway. So this is made, you can get this copy to look at later because I actually get it online. It was made available. Though is a PVT always is a confined it's a confined document, so you may not see a lot of it out there. So this is clients, country, feed, well, and the likes. So executive summary. So for MDT, the two water, two air sample from well, all those information, you begin to appreciate them. Then it has table of content where you talk of introduction fluid sample experiments program, the results, quality check of, you remember quality check, then the composition, then single stage separation of reservoir fluid, constant mass expansion. I said it can either be a constant composition experiment or constant mass study, or even in this case now it's constant mass expansion. So the naming varies. So the viscosity of reservoir fluid, then two separate stage separators. So obviously what they did here is just constant mass expansion. They didn't do DLE and they just moved straight to two-stage separator. So that's how it is if you look at those information. So that's how PVT reports typically look like. So I want to see, running out of battery? No. So that is it. So this is composition of the reservoir fluid. This is a mole percent of it, of nitrogen, of like I said, you can see this is 36 plus. This is the lump sum of it. So that is it on the PVT. So you can just check online and just look for PVT reports and you'll be able to appreciate what we've been discussing earlier better. So I'll continue to the last phase of the presentation. So yes, moving forward. So I believe that at the end of this presentation, like at this point, you've been able to understand what is saturated and undersaturated reservoir. If you see, you can be able to explain to anyone, to call your colleague, to someone below your level. So identification of different PVT parameter trend. So all those trends that we discuss, if you see it, you can actually draw it, you can identify it. If you see it, then you have a knowledge of CCA, DLE separator test, then simulation, black oil modeling, and equation of state. Then you have a grasp of a PVT reporting template. You've seen a PVT, you see what it actually contains. Then I will leave you with this: maximizing API gravity and achieving a low oil formation volume factor and reduce gas solubility will enhance recovery efficiency, boost profitability, and improve crude oil flow through the reservoir and pipeline. So you want to have as low as possible value of BO. You would want to be able to recover close to what you have in the reservoir. That's what it's talking about. Then the gas solubility, you wouldn't want more gas to be present in your oil so that you can have a large volume of oil produced. Then also you want to get your API as high as possible. Remember, an higher API means your oil is light, so it will reduce your cost of operation and whatever it will be. A lot of things need to be put in place when you are producing maybe asphatic oil, a very heavy oil in the range of 20-degree API, 10-degree API, and the likes. So, um, with this, I've come to the end of my presentation. So I'll be glad to take your questions at this point. Thank you so much.
Living. Hello.
Yes, yes. Please, you can go ahead and take.
Okay, so are there any questions? I want to confirm if you have any questions, please drop them in the chat box or raise up your hands. If you have any questions or any comments, if you don't have questions, this will aid or let me respond to all of them. And if you have no questions, I'm seeing the chat box, somebody's asking if this was recorded. Yes. Okay. There's a question from Aboyemi Dibis. In the CCE, what helps detect gas release? Could you respond to that?
Come again, please.
In the chat box, somebody has sent a question. In the CCE, what helps detect gas release?
Okay, so if I can get you correctly, perhaps you're trying to ask if for the CCA and you are trying to determine bubble point pressure with is that what you are trying to ask? At what point do you get your at what point do you get to see or detect your bubble point pressure? Is that what you're asking? Okay, you said yes. Yeah, this is a PVT cell. You cannot visually detect your gas, even if the PVT cell is transparent. So there's a device in a PVT laboratory that can actually show you that, okay, this is there's presence of gas. A presence of gas has been detected. So there's a device for that in the PVT laboratory. Yeah. So you can visually detect that. Please, does that answer your question?
I think he's responded yes, yes, yes. And then, yeah, I think that's all the questions you have. Okay. Abdul Hafiz have sent a question too. Is there any factors that determine which technique to use between CCE and CMS?
Okay, thank you for that. So I just want to, I'll just throw a bit of light on that. CC and CMS, they basically do same thing. So what the difference here is just the way the company decide to name it. So it's either constant composition experiment or constant mass study. So it just basically depends on if Cypher Crescent I choose to in Cypher Crescent if I choose to name use CMS, other people may decide to use CCE. So it's just nomenclature. So they still mean the same thing and it's still the same test. So you still use the same technique. Please, does that answer your question, sir? All right. I'm saying thank you then. So do we have any further question? So I believe maybe at this point, I believe everybody, maybe we understand to some extent. So can you just drop whatever, maybe one thing that you actually gain from this session. Can you quickly drop it in the chat box while we wait for? So quickly drop one thing you learned here today differently. Perhaps you've been hearing about PVT, then drop one thing that you learned differently from today, from yesterday's session. I'm not saying anything yet. Does that mean that we did not learn anything? Drop it, drop it, drop it, drop it.
Thank you, thank you. I want to believe
Yeah.
that. Okay,
Thank you.
I'm seeing comments already.
Yeah,
Okay,
yeah, I'm seeing that too. Yeah, exactly. You don't necessarily need to get information from there. So it's compositional analysis that depends directly on that. You need information from your lab experiment to go forward that in your equation of state modeling. Thank you.
Okay, thank you so much. Thank you so much for taking our time. We can give our speaker some virtual applause for the phenomenal time he took to answer questions and, of course, give us this amazing discussion on PVT analysis. Ladies and gentlemen, we come to the end of this 2 days session. You're still advised to go and join SPE if you have not joined. There are several student members benefits. And if you're a YP, you need to renew your membership if you have not. Ladies and gentlemen, I saw a question on the chat box if this event was recorded. All of our virtual sessions are live on YouTube. All you need to do is go search for SPE Abuja section on YouTube, and you'll find today's session, you'll find yesterday's session, and all of our past webinars live on YouTube. If you will need information on our events which will happen in the future, please endeavor to visit LinkedIn, Instagram, YouTube, Facebook, and of course, Twitter, now called X, and you get information on SPE Abuja. We switch gears and wrap up the events by having a vote of thanks by our Assistant Student Affairs Chair, Chinaza and Were. Would like to hear from you, Ma, as you wrap up the event for us, Ma.
All right. Good evening, everyone. Thank you so much to our speakers for teaching us well. Yesterday, when I was inviting people for today's program, I told them that yesterday we had a phenomenal a knowledge-packed session, and that today was going to be a phenomenal one. And from what we've seen today, I believe everyone can attest to that. Personally, I have learned a lot, and I'm sure everyone on this call can say the same thing. So to our amazing speakers, thank you very much. I would also love to appreciate our section chairman, although he's not here, Dr. Ikechukwu Okafor, and our student affairs chair, Aisha, for putting this together. Thank you to every student present. Thank you, Akpan, for the moderation. Thank you, everyone, for making our time to be here. Do have a restful weekend. Thank you very much.
Thank you, ladies and gentlemen. Thank you, Chinaza. Thank you, Aisha. Thank you to our amazing speakers. Thank you, Cypher Crescent. Thank you to all of our students from ATBU, AUST, ABU, Bayero University, Bayes University, Foots Mainland University, Unimate, and of course, Uni Abuja. We sign off for today. My name is Ofofonono Akman. My pleasure it is, as always, to serve as your master of ceremonies. Bye for now.